Before watching this video on example 17, you want to make sure that these ideas are starting to feel more concrete, because this is going to be a much more challenging version of those same examples. Really what's going to happen is we're just going to apply the same process but with more than one iteration. So we're using the same ideas, just a lengthier version of the problem. To save some time, we're going to skip through some of these earlier steps a little quicker than we have been. We know we should be looking for 4 real zeros. The signs test would tell us that we'd be looking for 1 positive real zero and either 3 or 1 negative real zeros. And we would get a list of values for P over Q that would be equal to plus or minus 18, plus or minus 1, plus or minus 9, plus or minus 3, and plus or minus 6. Again, we would use those values for P over Q, substitute them into the function k of x until we get one that gives us an output of 0. That would happen if we substitute in x equals negative 2. So k of negative 2 would give us a function value of 0, telling us that x equals negative 2 is a 0. From there, then, we would take k of x divided by x plus 2. The result of that synthetic division would give us x cubed minus x squared plus 9x minus 9, meaning our function k of x can be rewritten as the quantity x plus 2 times x cubed minus x squared plus 9x minus 9. Again, we've skipped over some of those steps that we've reviewed multiple times through these previous problems, but we would want to actually carry out the steps of synthetic division to get that result, so that then we can focus on the depressed equation, which we'll call, again, d of x. Whatever we have left over with that depressed equation, we just need to continue applying some approach to factor and find these real zeros. If we have a quadratic, we can look at factoring it directly. We can apply the quadratic formula. In this case, we have something that we can't factor directly, but what we can do is go back to our list of potential rational zeros. It could be negative 2 that we find as a factor again, but we would plug in this list of values. And I actually just realized that I left plus and minus 2 off that list before. So negative 2 only works if it was in that list to begin with, which it should have been. So we go back to that list of values for P over Q, substitute them now into this depressed equation to see when we would get a result of 0. That would happen if we used x equals 1. So if we were to evaluate that depressed equation at 1, our result would be 1 cubed minus 1 squared minus 9, plus 9, and then minus 9, or 0, which tells us that x equals 1 is a 0 for d of x, that depressed equation. If it's a 0 for the depressed equation, then it's also a 0 for the original function, in this case, k of x. So we'll move on to our next step, which would be taking that depressed equation divided by x minus 1. In this case, that would mean setting up a synthetic division problem with d of x as that function inside that division notation. Giving us 1, 0, 9, and 0 as our remainder. which tells us that d of x can be written as x squared plus 9 times that factor x minus 1. We can include this in our factorization of k of x. We already found that x plus 2 is a factor, and where we originally had that depressed equation, we'll now swap in x squared plus 9 times x minus 1. This already gives us very clearly two of our factors, or two of our zeros, which would be -2 and +1. So what's left is for us to find out the zeros for x squared plus 9. Subtracting 9 over to the other side and taking the square root of both sides would give us plus or minus 3i. We can add those two factors to add those two numbers to our list of complex zeros, and then we can write out the full factorization for our function k as x plus 2 times x minus 1 times x plus 3i times x minus 3i. Again, just to walk through what we did here, we started off with the same approach that we would have applied originally. We found that x plus 2 is a factor of that original function, so we divided to get a partially factorized version of k. From there, we focus on what we can do with that depressed equation. In this case, that wasn't something we could factor directly, so we went back to our list of potential rational zeros, found one that plugged into that depressed equation, gave us a value of 0, divided again to give us a factored form for that depressed equation, which then let us continue factoring and finding all real zeros for that original function.